start right now.
Next week.
Week 7, so we have this week and then 2 more weeks, and then we're done. I want to give you guys 3 weeks for finals, also for myself. So this is the 3rd to last. So we're in the home stretch. So after this, we're going to be going all about, we're going to talk about convolutional neural networks. And then the next 2 weeks, we're going to be focusing on creating our attention mechanism, which is going to be as a supplement to what we learned today. So why convolutional neural networks? So if you guys remember last week, we talked about like basic neural networks with a bunch of circles and lines. Oh, can I get markers, Jamal?
Yes.
Thank you very much. We talked about we talked about neural networks, and you guys hopefully you guys watched the video that I posted up. That was homework for 2 weeks ago. Thank you very much. The circles, with the more circles, and yada yada yada, where every single of these nodes are connected to every single of its subsequent neighboring node. This is great. It's a universal approximator, as if you guys watched the YouTube video. The issue with this is that while it's great for generalizing for any task, it's very computationally expensive, especially once you increase the input number. So right here, the input number is 3, as indicated by these 3 circles. But data in real life is always going to be bigger than that. In this example, we have an image, and this is the actual dimensions. It's a 642 by 350 pixel image, which means that this is going to be the number of inputs for our neural network. This is obviously way too big. Actually, this number isn't even right. Why would this number, this itself is right, but we need to add an additional number, an additional dimension, because this is a colored image. Do you guys remember what number we need to add?
RGB?
Yeah, RGB, so 3. So this is the actual number. If we were to turn this into a input for our machine learning model, it would be RGB, R, and that's just for red, green, blue. So the first matrix would be a matrix of how deep the red is, then the green, and then the blue. So those are 3 matrices. So this would be like humongous. So to solve this problem, we would need to introduce an idea called a convolutional neural network. This model does use the neural network that we talked about last week, which is going to be right here. In most machine learning papers, they don't actually call it a neural network. They call it a multi-layer perceptron, or an MLP. But this overall network, this overall architecture does use an MLP. It also has 2 other really important layers. Convolution, which is where the name is from, and then pooling. And then this is also followed up by an MLP. This is what it looks like. Some of you guys may be familiar with it, but basically we have our MLP, or the neural networks that we discussed last week, on the right-hand side. And then we have all this extra fluff that we'll be discussing in this class today. Generally speaking, what we're doing is taking our input image. We are trying to get as much important information from it as possible before going into this layer. Generally speaking, we need a way to downsize. So as you guys can see, we have a 28 by 28 by 1 being the dimensions. I like to put the 1 here, like 1 by 28, but this image from Google Images has it like this. And then the layer before the fully connected layer, we have a 4 by 4 by n. N is like the depth, or the number of matrices, or the number of features, number of features, matrices, whatever. This 4 by 4 is obviously a lot smaller than 28 by 28. So we need a way to downsize our original input image while extracting meaningful features, and these features are going to be indicative of whatever we're trying to predict. In this case, we're trying to predict the number 2. So hopefully all of this stuff here has enough salient information so that we could correctly predict that this input is a number 2. And as per the previous slide, we have convolution and then pooling layer. Here we have this whatever this thing is called. This is going to be the process of convolution. After the process of convolution, you guys could ignore this right now. Just know that from here to here is the process of convolution. From here to here is called pooling. Pooling is always a method of reducing the size of this to this. So this is 24 by 24. This is 12 by 12. And we're still keeping the N1 and the N1 here. So the number of channels from this part to this part is the same thing. All we're doing is shaving off this 24 to this 12, cutting it in half, essentially. So that's a way, or that's how we're going to be reducing the size, and we'll go over the math eventually. But this is a general idea. And so some people, some professors, or some like researchers will call like this as a convolutional layer, and then someone called this a convolutional layer. So in this architecture, we have 2 conv layers, and then finally the MLP layer. Doesn't really matter like the structure. Most architectures are very similar. They follow this basic format when it comes to a CNN. Any questions on like the architecture so far? Yes, Tony?
In this diagram, aren't there 2 MLP layers?
In this one, there is 1.
Oh.
So all of these matrices get flattened.
Mm-hmm.
So this first matrix gets flattened, and then the next one gets flattened, and then they get concatenated with each other in the back end.
Yeah.
And then all of those vectors that are concatenated are going to be used as the input for this MLP layer.
Oh.
And then the second layer is not an MLP layer. It is technically, but it's the output layer. It's the prediction.
Okay.
So the code for this would just be 1 linear layer.
Okay.
Yeah. Oh, wait. Okay, convolution is a process. I've always liked using this analogy. So the light blue is our image. The dark blue is like a pair of binoculars. So for this pair of binoculars, we're going to start at the upper left corner, and then it's going to zigzag across the entire image, and it's going to finally end at the lower right corner. So what we're doing is we're taking a pair of binoculars, we're scanning an image from top left to bottom right, and then once we do that, we get a feature. Now a feature is like a very abstract, like concept, I guess. If you have a picture of a house, it has windows, has a door, maybe it has a car even, but what you want to do is predict that this is a house. A feature, in this example, could be like the walls, or the floor, or it could be even like the door, right? So I have my pair of binoculars, and I'm scanning through, and then with each different pair of binoculars, I get a different feature. Maybe with one pair of binoculars, I get the walls. Another pair of binoculars, I get a door. Another pair, I get the windows. Stuff like that, right? And this is why we have the depth here. Because we can dictate as engineers how many pair of binoculars we have. If we have n binoculars here, we get n features. If we get m or k binoculars at this level, we're going to get k features, and so forth and so forth. Of course, now you guys are probably thinking like, well, why don't we just do like a gajillion pair of binoculars here, or then like a bajillion times 2 binoculars here? Well, there is going to be a point where your model is so complex and you're just getting so many features that like it's pointless, and your model's going to overfit. So there is a difference of compute and accuracy, and you have to find this balance. Now, what this balance is up to the engineer, and that problem is called optimization. Well, outside of backpropagation, just the process of optimizing your model is literally its own field of study within machine learning.
going back to this example, we have three matrices essentially. We have our input data, which is a matrix. We have our binoculars, which itself is a matrix. And then our output, which is then going to be another matrix. Three matrices. Input data, and then our pair of binoculars, and then our output. As per this. Matrix, matrix, then the thing that's turning it, this rectangle here, is another matrix. Any questions so far? Cool. Now the actual math is very, very, very simple, in my opinion. Imagine we have our input data, which is here. We have our kernel. Our kernel is going to be called a pair of binoculars. Kernel is also called a filter. So the word filter and kernel are interchangeable. And then our output. So this is a 3x3, ABC, ADG, right? Kernel is a 2x2. Output is going to be a 2x2. The math is we take our kernel, our pair of binoculars, put it in the upper left corner, and then this A is going to be multiplied by this U. This B is going to be multiplied by this B, so forth and so forth, and then add to each other. So extracting information from this A and this U is going to determine how much information we want to extract from this A. This V is going to determine how much information we want to extract from this B. And then we keep doing that for DW here, and then EX here, and here. So that's going to be this part right here. From there, we add all the numbers together. Adding is different than multiplying, because with adding, you're not losing any information. When you're multiplying, you can lose information. If you multiply by something, that's between 0 and 1, right? With adding, you're not losing anything. And then we do the same process. So we shift our binoculars to the right, and we do the same exact process, and we get that number here. Do it again, and do it again. And then that's going to be our output. The numbers in this kernel are going to be called your parameters. And as mentioned last week, in back propagation, the numbers here are initially randomized, and then eventually your model is going to learn what the appropriate number should actually be for U, V, W, and X.
Question. So would E be overrepresented?
Would E?
So it's like, since like all of them are being multiplied, right? But then E is being scanned like 4 times.
That is great intuition.
And then like underrepresented would be like A, G, C, and I.
That's perfect, bro.
How's that accounted for?
Yeah, that's great. So we will be talking about that, but I'm really glad that you brought that up, because as you guys can see, E, D, and F, even everything besides the pointer, besides the edges, are going to be scanned multiple times. B is going to be scanned twice, D is going to be scanned twice, but then E is going to be scanned 4 times. So what if the information at these edges are just as important as the information in the middle, especially this E? For example, like an EEG signal, right? What if the data point here is the same, is the equal importance as the information there? Or stock prices. Let's say we have stock prices from like 5 years. What if this number, the last number, and the last number there are equally as important as all the ones in between? We need a way to make it so that the information has equal weights for our machine learning model. Because right now it doesn't. In this basic example, it does not have equal weight. But we will discuss that soon. So, like I mentioned, in back propagation, when we do this, and this is going to be our input, this matrix right here is going to be one of the matrices here. And if this doesn't have good information, then during back propagation, our parameters, these numbers here, are going to change so that we're decreasing our loss, as we talked about last week. Oh, any questions regarding the math or anything here? Cool. Also, for you guys who will take linear algebra, a convolution in linear algebra that you guys will learn in school is different than the convolution that's used in here. Just a heads up. Okay, so we're talking about like abstract features. This is one very clear example. Now, whether the machine learning model is actually doing this or not, I don't know. But there is a way to run your model through a CNN and then pick up on the features. For Tawny's project, she's using like EEG signals and using spectrograms. So I don't think the features would be like this, like visually understandable. But you guys can still do it. Anyways, we have our data, which is here. We have the kernel, which is going to be these lines. This is going to be this. And then we get features. In this example, we get vertical and horizontal edges. And you can predict whether this picture is a picture of like a city or a beach. For example, this is probably a city. So that's what the model is going to guess with these features. And this is the process. We have any number of kernels we want to get any number of features from those kernels. In this example, the vertical edges will have a kernel that looks like this, and then the horizontal edges, this one, would have a kernel that looks like this. And these kernels are going to be placed here, right? So these are the things that are going to be sliding over your images, your binoculars. And this is how you extract features or extract meaningful features. And of course, like I mentioned, these numbers are the parameters. So these are subject to change based off of the chain rule and partial derivatives. Input image, and I have two kernels. Using H and W, what's going to be my output shape? If I have an image and I'm going to be running it through two kernels, what would be my tensor shape? What would be the output shape of my tensor using H and W?
Is it 2D?
Talking about dimensions?
Yeah. So after this, I'm gonna have a tensor or like a 3D matrix. Using H and W, what would be the output shape of a process of my input image going through this kernel and then going through this kernel? No, it's not as complicated as you guys are probably thinking.
It's like h minus 2 times w minus 2.
Basically, each
No.
kernel you're starting at the top left and you're sliding it. So you're taking like a 3x3 in the original, and then that 3x3 turns into like 1.
Oh no, I'm not asking for the exact H and the exact W. We'll talk about those afterwards. How you compute that. What I'm asking is, if I have an input image right here, and then I have a kernel here, and I go through it, do some math stuff, I get a tensor. And then I do the same thing here, and I get another tensor.
Is it 3x3x3?
No. Using H and W.
Oh, H.
So basically, here's what it'll look like. This by H by W. What's this number?
3?
Is it like h minus 2 times w minus 2?
Oh, is it 1?
No, no. So
So it's black and white?
I'm not. That's a good guess. But no. So the question is, I have two kernels. So I initialized like my machine learning model as two of these, and both of these are gonna go through this, and then I'm gonna have a tensor at the end of it.
Yeah. So you're asking for the output shape.
Yeah. So we know it's height by weight. What's this number?
It's the number of layers after.
Yeah. So we have. It is the number of layers.
Mm-hmm.
Yeah.
Would it be 2?
Yeah.
Okay.
Yeah. Very simple. Yeah. I don't know. I'm not like I don't know. It wasn't a trick question, obviously.
Okay.
It wasn't a trick question. I think I could have asked that better, but it is 2. Yeah.
So that 2 is just the number of kernels.
Yep. There's the number of kernels. Yep. So in general, we're going to have a matrix. I'm sorry, a tensor at the end of every convolution. That's going to have a dimension of height, or it's going to have a dimension of the number of channels, or the number of kernels, or the number of layers, or whatever we want to call this. We'll call it C for channels.
Mm-hmm.
And then height and a width.
Why not just kernels?
For this,
Mm-hmm.
Because the research papers that we're going to be looking into next week call it channels for some reason, I believe. This one. Let me see. So I mean, I want to give you guys different vernaculars so that you guys are familiar with it. Once you guys look into your own research papers. But yeah, see, this one calls it channel attention. So, but they also call it feature map, which is what it is as well. Each channel of a feature map. So it's like feature map, channel. It's all the same. They're interchangeable. I don't know what people make it complicated. I don't know why, but you have your height and your width, which is going to be like just one of these. If you have multiple of these, that's going to be the number of channels, the depth of your Rubik's Cube of information.
And then the more you have, the more features that pretty much eventually bring out the picture.
Yep, exactly. So like this first layer in this example, if we go back to the house analogy, this feature could be the windows, and then this one could be the roof, and then this one could be the background or whatever. And you know, if you have more of these, you would think that the information would be like better, but actually this could produce. So back to our house analogy, this could be like a car, which just sucks. Like we don't need a car to predict that this is a house. This feature could be like the windows, which is good. That's indicative of a house. So like there's a sweet spot between too many features or too much information, and like reeling it back in so that we're ignoring the noise. How we can ignore the noise is how we ignore or silence noisy data and extrapolate more meaningful features is something that we'll be talking about next week. Okay, back to Cyrus's interesting point. There's a thing called padding, and it's literally padding the borders of your input data matrix with a number. The most common type of padding is called zero padding, which is what we're doing here. Another popular one would be mirror padding, where the numbers would be mirroring. So this would be 0, this would be 7, this would be 4. You'd be mirroring the number that you're adjacent to. 0 is the most common because you're not adding any additional information. You're just like providing a 0. And it's the same thing. You'd be taking this kernel, but instead of taking the kernel here, you'd be doing it here. This way, all the numbers have an equal has the same weight as any other number. Edges such as stock prices or EEG data, the beginnings and ends would be just as informative. This could be a good thing, this could be a bad thing. Another thing about padding that's really important is that, as you guys can see, we originally have a 6 by 6. Now we have an 8 by 8. Once we run a filter through it, in this example, we have a filter that's a 3 by 3. The output shape is going to be the same thing as the input shape, which is really important. In a lot of advanced CNN models, a lot of it requires the same output shape. So padding is the way to do it. Any questions on padding? Cool. Oh, yeah, sure.
So, when you multiply the 8 by 8 by the 3 by 3, as a result, you get 6 by 6.
You aren't multiplying the 6 by 6 by an 8 by 8. Rather, you're turning the 6 by 6 into an 8 by 8.
The 8 by 8 by the 3 by 3.
Yeah.
Okay.
So basically, just add another wall, like outside picture, to enlarge it to 8 by 8 at first, and then you plug in a 6 by 6 because it's gonna return to 6 by 6, which will change the same as before.
So like a case like there's a model called DenseNet that I actually would, if you guys want to challenge yourself in terms of like coding, you guys should code this out. It's a very interesting problem to solve. but it requires all the same matrix shape. So you would need to do padding for all of these. The size of the padding matters. How you're going to be concatenating them matters. So for Tawny's project, this would be a very interesting model for you guys to code. Look into it. Theoretically, it's a very simple model, but once you actually like code it out, it's like a pain in the butt. But if you guys have time, you guys should do it this semester. What was your question, Abby?
So the padding is going to make like each like feature have its own weight or like equal weights.
Yeah, so every single number now, like within here, which is our actual data, is going to have equal say in the final output. Because here, if we go back to here, this A, C, G, and I are only going to be mathed once. This B is going to be mathed twice from this kernel, and then when it slides over, right? And this E is going to have even more emphasis on the overall output, this overall matrix, right? So we need a way to say, hey guys, all the data should have an equal weight. They should all have an equal emphasis. So that's what padding does.
So there's just like more things to slide over, and so that more of like the A, C, G, or I can get counted for.
Yeah.
Okay.
It's more of the zero or the same data though. Isn't that, it has to be that, right? It can't just be anything.
Yeah, so like as Jamal mentioned, most of the time it is a zero. We do so, and that's another thing too, where like zero, obviously it's null, it's nothing. However, there is a thing where if you're sliding on the edges, you're getting a lot of zeros. But if you're sliding over here, you're still getting like numbers. So there is an argument, another way to do padding instead of doing zeros would be to, like I mentioned, to mirror the number that's adjacent to. So all of these would be a 3. This would be a 6. This would be a 7, 0, 4, 4, 4, 0, 4, and so forth. So that we can have some like information. Because a 0 does kind of like negate a lot of the information. You know what I mean?
What if you do something like, okay, instead of 0 you do 1,
You can do 1.
and then do say 2? What are you gaining, or what are you changing when you go up in scale like that?
That's a great question. Mathematically, think about what's happening within the convolution, and think about how that would affect the overall output. What do you guys think? If I were to instead do 0, if I did 1, for example, how would that change the output? Think actually do the math. Like how would that change?
Just bigger number.
Yeah.
Increase.
Yep. So you're gonna be increasing the numbers, right? So if you do a 1, it's gonna be higher than obviously 0, and so forth and so forth. And if we look back at like, for example, a sigmoid function, just any typical number where, wow, let's do, okay, I can't zoom in. Hope you guys can see. The higher the number is, this is the x-axis. This is our input or our dependent variable, and this is going to be our output, our independent variable. The higher the number is, like, I don't know, even up to like 2.5, the model is like, dude, this is so close to 1, or at 2.5, the model is so close to an output of 1, and vice versa. If our number is like negative 2.5, we're going to say it's very close to 0. So the smaller the number is, the more it's closer to 0, the higher the number is, the closer it is to 1. You would think that's good, but in your situation, if you did a padding of 1, we're going to increase that number a lot, right? And if you're going to increase the number a lot, it's going to be more confident that the model is closer to 1. So maybe 1 is Alzheimer's and 0 is healthy. So you're saying that this feature, this MRI image, this input data, is very close to Alzheimer's. But that's not necessary. It doesn't have to be true. It's just that you're padding it with a 1, so you're adding it a lot. And then if you do a padding by 2, you're going to be doubling it, essentially. So you're going to be saying it's even more confident that it's Alzheimer's. But mathematically, that might not be the case, right? Generally speaking, you want numbers like, generally speaking, you always want your numbers to be around like here. You know what I mean? Because of how close the prediction is. It's great if your model is confidently correct if it is Alzheimer's, but if it's confident about having an incorrect prediction, it's going to be very hard to get that MRI image back to here. You know what I mean? If it's just like stuck here because it's a very high number here.
So it's almost like you're influencing it.
Yeah. Exactly. There's a really good. I don't know. Okay, yeah. Geometrically speaking, what's really happening in machine learning is we have a normal distribution of, let's say, people with Alzheimer's, A, B. And then we have a normal distribution of people with Alzheimer's, healthy. And so this is a gap that our model struggles in. You could think of it as the model is trying to minimize this space as much as possible while maximizing the gap between them, right? You want to live in a space. This space is this, like dead center, right? So and if you split this space up, you're able to discriminate between these two better. However, if something is like a healthy control here, it's going to be extremely hard to get your model to predict this data point as healthy if it lives here, like if it's like over here. So you would want, it's like a double-edged sword. You want most of your data to live in between so that your model could discriminate, but you also don't want it so that it's like confidently wrong. You know what I mean? Yeah. So that's why we do padding of 0 most of the time, because you don't want to like create too large of a number. Yeah. Great question though. That's a good question. So that's what padding is. Any questions on padding?
But the numbers like in the middle is always like the most time that calculations happen. So that means the numbers in the middle will always be very high.
Yes. Most likely. I mean, depends on your data, right? We have MRI images. So our images look like this, with like a brain here. So naturally, we're gonna have like numbers here, and we're gonna have like literal zeros all around. It really just depends on what kind of data you have. But yeah, I mean, for the purposes of this class, yeah. And then after we do a convolution, what occurs is a activation function. Activation function is something that breaks linearity. Sigmoid is one of them. This one is a ReLU function. This is the actual function. We use ReLU because of a few things. It's extremely simple, and also because the derivative is extremely computationally efficient. Like I mentioned, in backpropagation, we have to take the derivative. If we're using this as our activation function, when we move our data back with backpropagation, we have to take the derivative of this. I don't even know the derivative of this. I guess it's this. I mean, I could probably figure it out if I like focused, but the more math stuff there is, the more expensive the computation. Computation is something that a lot of like state-of-the-art frontier AI labs brag about. They're like, oh, like 500 billion parameters, or 500 billion like flops. I was telling Tony, like a flop is called a floating point operation, and it's a measure of how much math, literally plus, divide, minus, multiply, is happening in a model. The So the higher this number is, the higher number of parameters a model has, the more it could understand complex data. So it's kind of like a measure of it's a measure of complexity, I guess you could say, for a model. But on the other hand, it's also a measure of computational expensiveness. And these big companies have partnerships with like Google and stuff like that, so they have access to all the good stuff. But computational efficiency is something that researchers who don't have these resources have to worry about. So going back here, this is a very simple function, and so we like a lot of researchers like using this. So this function right here would be applied to these numbers as the output. Convolution and then activation function on this. So it's not going to change the shape of the tensor at all. Rather, this function is going to be applied to every value, every ith value on a matrix. Pooling. Pooling occurs, so in the typical architecture, you can have a convolution and then you can have an activation function and then you can do pooling. You can also do convolution and then pooling and then activation function. There's no rhyme or reason to any of it. It's just like what other researchers what they suggest. Yeah.
Going back to the convolution, what do you mean by break the linearity? Like, how does that like help us better like basically?
Yeah, if we have data, this is like a geometric interpretation. If we have data and our data looks like this, then most of the time data does look like this in real life. It's never gonna look like this, which is we can use a linear regression with this and draw a line. And so if a doctor is like, well, what's gonna happen here? You can just look at the line and be like, oh, well, our prediction is gonna be this y variable here. Data never looks like this. It's almost gonna look like this, especially with machine learning, predicting Alzheimer's or predicting the next word, like in LLMs. So we need a way for our line to go like this, right? This is breaking linearity. We're literally making it so we're not drawing a line, we're drawing a squiggle that could go through our data. And this is the idea of like a universal function approximator from the YouTube videos that I showed you guys for the homework. It's like we need a way to model any kind of data, and if we want something that can model any kind of data, we're going to need to break linearity. Yeah. And this is just one of the functions to do so. Okay, cool. Pooling is the same idea of a convolution where we have a kernel and we have the size of it. And we're going to introduce a concept called stride. Stride is literally how far your kernel is going to move. So we have this kernel here. And notice how there's no this, right? There's no numbers. But we still have a kernel as per this blue thing. That's a 2x2. We have a filter still. This filter is not going to do any math stuff. I mean, it is, I guess. It's going to take the max. What's the maximum number here? It's 9. We put that here. Move it 2 times as per the stride in this example. We have a stride of 2. So we're going to, instead of moving from here to here, that's a stride of 1. We're going to be having a stride of 2, which is going to be moved to here. And then same thing here, from here to here. And this is called max pooling, so we're getting the maximum numbers at every single mini kernel, mini matrix type of deal. And so max is a way of getting the very poignant and very I don't want to say important because the other numbers could be important, but just the numbers that stick out to us the most, right? So outliers. So this is a way of downsizing our data from a 4x4 to a 2x2 by getting the most poignant and outlier-ish data. The other way to do it is by taking the average. So average, of course, you would be nullifying those outliers, which could be a good or bad thing, you know, depending on your data. So that's another type of point would be to do average. Extract meaningful features, and the most important thing is to downsize. We are downsizing our matrix, our feature, our one feature, or all of them, while maintaining the integrity of the data as best as we can. And you can do that by pooling a max or average pooling. Any questions on pooling?
Why is it important to downsize?
It's important to downsize because if we go back to like